Hello, welcome to Zigmatech Learning Hub. I will be your instructor for physics. For this class, we are going to be taking our exercises from Examguide app. If you don't have the application already installed on your device, I will want you to download the app in order to follow along in this class. Examguide is a leading educational app that helps students prepare adequately for various exams like UTME, post-UTME, WAEC, JCE, KCPE, IJMB, JUPEB, KCPE, BECE, JSCE, NCEE, NECO, etc. You can download the app from www.examguide.com or Google Play Store. Please subscribe to our channel and turn on the notification bell and get updated on new videos. Are you ready for this class? Okay, let's get started. Welcome to physics class, and today we are going to be looking at specific heat capacity by electrical method. By the end of this lesson, you should be able to define specific heat capacity of a substance, explain the electrical method of determining the specific heat capacity, and solve problems on specific heat capacity by electrical method. When we talk about specific heat capacity by electrical method, we are just trying to let you know that from this experiment, or from this drawing, that we can have a circuit such that in this solid block, look at this one, this is a metal block, and this is lagging. What do we mean by this lagging? Look at this line. This line all represent lagging. What is lagging? Lagging is simply a material which is used to prevent heat loss or heat gain to the surrounding. The surrounding of this diagram, so that the heat from here will not be able to enter inside here to affect the temperature of this substance. Neither does the heat inside this place should go outside. So what we mean is that inside that container, the heat there should be constant. No heat should come in, no heat should go out. That is the essence of this lagging. Now, this is a metal block. This metal block, what we use it for, we just want to increase the temperature of the metal block, probably for something else. And that method of heating this particular substance is the electrical method. That is why in this place is a voltage supply, or which is a cell or a generator, which is supplying energy, or a current, which is this place, which is the ammeter, which is measuring the quantity of current coming into this system and the voltage between the points. Then inside here is a coil. Look at this place, is a coil. What that coil does is to, or we call it heater. What it does is to, the energy from electrical energy is converted to heat energy with the help of this metallic substance called coil or heater, or the ring, the one you use for boiling water in your house. So this whole essence is just for us to be able to determine the specific heat capacity of this solid material by a method called electrical method. Now remember, in other class we also learned specific heat capacity by mixture method. We've learned how to find the specific capacity by mixture method, and today we're going to concentrate on electrical method. And this few explanation can only paint the picture of what is happening. And let me also just give you a little analysis for you to be able to understand or drive home my point. It's very simple. You connect, let's assume that this is a switch. You connect a wire from this switch then to your coil. So this is electrical energy from the switch. And then let's assume now that this is a bucket, and this bucket is filled with water. All right? As this bucket is filled with water, this is a container, and then this is water or liquid. Let me call it liquid. It could be anything. And this is the heater. So what happens there? The electrical energy from the wire, from the mains, is converted to heat by heating this liquid. And at the end, what is our intention? is to find the specific heat capacity of the liquid in this container. This is for the liquid. What you are seeing on this place can also be regarded as finding the specific heat capacity by electrical method. Also, let me also show you this diagram. Look at this picture on this one. This is aluminum pan. That is the container, and inside is the water. What happened? Look at the low voltage supply and this electric heater. So this is the electric heater, and this is the thermometer. To do what? To measure the quantity to measure the temperature of the liquid. So these are just a few processes of finding the specific heat capacity. So in this class, what we are going to do is determining the specific heat capacity of a solid by electrical method and determining the specific heat capacity of a solid by electrical method. Now the question is, how do we do it? You know, so many textbooks will come up with a formula they want to give you that will help you to achieve it. But let us look at them. If you have, I want to first start on this calculation. Let me put it this way. Calculation, or let's say derivative of the formula or equation. So the first thing you have to do is electrical energy is given as IVT, right? So how does that mean? Or let's say work done by electricity, W is equal to QV. This is what we know. You know, remember that in physics, we have different branches of physics. We have heat energy, and we have electrical energy, and we have different other mechanical energy, and all the rest of them. So now, all this energy have their own specific formula we can use to finding their work or their energy. Remember, if this is called, let me call it E, which is the work done by electricity. We also have ordinary work done by mechanical bodies, which we can call like force times distance. Are you getting me? So the work done by electrical method is different from the work done by mechanical body. It's also different from the work done by heat energy. So they are all different. But then today we are concentrating on the work done by electrical energy, and that is given as Q multiplied by V. Then what is Q? Q is looking at electrical energy, or we can call it quantity of charge. That is what Q is. Remember, it is measured in coulomb, and we can also say that V, this is called the potential difference between the points or the mains. So this one is going to be the PD, or people will normally call it the voltage. So that is what electrical energy is made of. We can also talk about power, electrical power. We say that electrical power is work done by electrical energy divided by time. And what is work done by electrical energy? The work done by electrical energy is given by IVT, all over T. T will cancel T. We now say that power is given as IV. So this is the electrical power. However, according to Ohm's law says that V is equal to IR. That means this can also be changed to say I bracket IR, such that the power of electrical energy, the electrical power is given as I square R. Sometimes we call it the loss in electrical power. So these are some of the derivatives we are going to use in this kind of explanation in finding the specific heat capacity of a substance, whether be it a solid or liquid. However, there is one more thing you have to understand. One more thing you have to understand is this: that energy is neither created nor destroyed, but converted from one form to the other. So if energy can never be destroyed, that means heat energy must be converted to electrical energy, or electrical energy must be converted to heat energy. These are going to be the principle that will guide us in what we are going to do today. So let's kickstart with one of these examples. Now, you said, how long will it take to heat 3 kg of water from 28 degrees Celsius to 88 degrees Celsius in an electric heater, taking a current of 6 ampere from an EMF source of 220 volts. Specific heat capacity of water is 4,200 joules per kilogram per Kelvin. So what are we going to do in this case? Let's go. In this area, we are going to consider the fact that the heater heated a quantity of water for a given number of time, which we don't know. Now, I know that electrical energy must be equal to what? Heat energy. This is the basic principle guiding what we are going to do. Now, if this electrical energy is equal to heat energy, the question should be, what then is this electrical energy? And remember what we said, that IVT is the electrical energy, and this is equal to MC change in theta, and this is called the heat energy. On this principle can we base this our explanation and solution. Now, what are we going to do? We have that the current I is 6 ampere. So instead of this I, I'm going to put 6 ampere multiplied by V is 220 volts. V is 220 volts multiplied by time, because I don't know the time. Now I know the mass. The mass of water is 3 kg multiplied by the specific heat capacity of the water, which is 4,200 multiplied by temperature change, means from 88 degrees Celsius to, from 28 degrees Celsius to 88 degrees Celsius. So that is going to be 88 minus 28. All right, let's take it one before the other. Now, I am going to make this look easier for me, because since there is no plus or minus separating this, neither there is plus or minus separating this, I'm going to cancel this and this. 2 into this is 11. 2 into this is 210. So 3 itself is 1. 3 into this is 2. Is 2 here. So we have 2 times 11 is 22 multiplied by time is equal to 210 multiplied by 88 divided minus 28 is going to be 60. So I have 60 here. Okay, 2 into this is 11. 2 into this is 30. So this is 11T is equal to 30 multiplied by this. 3 times 21 is 27. Let's say 21 times 3 is 3. 63. So I'm going to have 6300. So T is equal to 6300 divided by 11, and which is so we have 572.7 seconds. So this is the time it takes to heat this water of 3 kg from 28 degrees Celsius to 88 degrees Celsius in an electric heater if the current is 6 ampere. So let's go to the next question. Okay, we have another question. Let's keep going. I'm still going to keep this constant because this is all we have to be doing throughout in this calculation. He said, how long does it take a 750 watt heater operating at a full rating to raise the temperature of 1 kilogram of water from 40 degrees Celsius to 70 degrees Celsius? So the same thing we are going to do is that we are going to say that electrical energy is equal to heat energy. Now, electrical energy, in this case, we are not giving current and we are not giving voltage. We are asked to find time. But remember this, that power is equal to IV. So if this is true, instead of putting this IV, since it is not given, it's already been given in 750 watts. Now, how do I know that that is power, which is 750? Is because of that capital W at the back, and that is the unit of power, electrical power, which is given as watts. So I'm going to write P times T is equal to MC change in theta. The power is 750. 750 multiplied by time. I'm looking for time. I don't know what the time is. And the mass is 1 multiplied by, what is the specific heat capacity of water? Is given as 4200 multiplied by, what is the change in temperature? Change in temperature is always subtraction of the temperatures involved, the initial temperature before heating and the temperature after heating. And that is going to be 70 degrees Celsius minus 40 degrees Celsius. And that is going to give me, let me put it down for you to follow up. So we have 750 T is equal to 4200 times 30. So I'm going to cancel these 3, I'll cancel 0, will cancel here, 0 will cancel here. I choose to do this because there is no plus or minus separating this, and there is also no plus or minus separating what I'm doing here. So I have 75T is equal to 300612. So time is going to be 12600 divided by 75. So let's just find what that is. So I have 12600 divided by 75. So I have 168 seconds. So this is the time taken to do this. The time, how long, whenever you hear how long, it means the time it takes to heat water of 1 kilogram with the power, electrical power of 750 watts from 40 to 70. Now let's look at something that looks a little different. The power is still there again. 500 watt heater is used to heat 0.6 kilogram of water from 25 degrees Celsius to 100 degrees Celsius in T1. If another 1000 watt heater is used to heat 0.2 kilogram of water from 10 degrees Celsius to 100 degrees Celsius in T2, it says find T1 over T2. All we need to do is to follow the principle. That the principle is very simple. Now, if you consider this question very well, you realize that 2 different energy supply are involved. The first one is 500 watt heater, and the second one is 1000 watt heater. However, we are going to treat them one after the other. Now, the first one is P times T is equal to MC change in theta, which is the main principle we are working with. So 500 watts is here. I'm going to take them one after the other because remember there is T1 and there is T2. So this is going to be T1, and the power for this first time is 500. 500 times T1 is equal to, what is the mass? The mass is 0.6 times. What is the specific heat capacity? Okay, let me consider, okay, if this is water, the two of them are water, so I can just use C, multiply by, what is the temperature change? From 25 to 100. That means 100 minus 25, which is going to give us 75. Okay, so in T2, this is the first one. Okay, let's first take what the first one is going to give to us. So we have 500 T1 is equal to 45 C. So I'm going to have that T1 is going to be 45 C all over 500. So this is going to be 0.09 C. This is the first time for the first one. We are going to consider the second one. Now, in this second one, we have another power, which is 1,000 watts. So this 1,000 watts is going to be 1,000 times T2 is going to be equal to, the mass is 0.2 times C times the temperature change is 90, because from 10 degrees Celsius to 100 degrees Celsius is 90. So I have 90. So let me cancel here first. So I have 100 T2 is going to be 1.8. So T2 is going to be 1.8 divided by 100, which is 0.0018. 0.018. So now I have this is as T2, sorry, it must be with C. It must be with C. And I also have this one with T1. Now the question says I should find T1 all over T2. So T1 is 0.09 C and T2 is 0.018 C. So I'm going to have that T1 over T2 is going to be 0.09 all over 0.018. C will cancel C. And we are going to have so this is going to be 5 seconds in all. Okay, so we are going to solve one more question on this one, which has to do with combination of one or two of those quantities, because we have different quantities. We are looking at water, and we are also considering the container in which the water was put. So we are going to look at that. Now, a heating coil of resistance 20 ohms connected to a 220 volts source is used to boil a certain quantity of water in a container of heat capacity 100 joule per kilogram for 2 minutes. If the initial temperature of the water is 40 degrees, calculate the mass of water in container. Specific heat capacity of water is 4.2 times 10 raised to power 3 joules per kilogram per Kelvin, assuming boiling point of water is 100 degrees Celsius. So now, in this question, we have to consider that there is a heating, number one, and that the heating coil is now increasing the temperature of both water and the container. So what are we going to do? We're going to say that heat lost by heat lost by the electrical energy, yes? No, no. I'm going to say heat supplied by the electrical energy or the heating coil. I'm going to say heat supplied by the coil or heater is equal to heat gain by water plus container. So this is what happened. Because in this case, you have to accept that fact because the coil is now transferring energy into water and then the container. And the container is not negligible at this point. So let's get it started. So the first one is that IVT is equal to specific heat capacity of water, mass of water, specific capacity of water, times temperature change of water, plus what I have written is the quantity of heat for water. That is heat gained by water. So I'm also going to do another one, which is heat gain by the container. And that is going to be the mass of the container, specific capacity of the container, and change in temperature of the container. And all these two, they are equal to the heat energy or equal to the electrical energy supplied by the heater. Now we are given resistance and volts and then time. What else are we going to do? Because the time is given in 100 in minutes. I'm going to say that since there is no current, I'm going to say I bracket IR multiplied by T. What is IR? IR is the voltage. And then the I is the current. Okay, all I have to do now is to make sure that I remove this I because there is no I there. There is no current. So let's do a little, let's play with it. Let's do a little derivative. Now remember that V is equal to IR. Now that means that I is equal to V over R. All right? So in this case, I'm going to remove this I. I'm going to say that instead of putting I, I'm going to say V times V over, this is I, which is V over R, multiplied by this V, then times T. So at the end, I'm going to have V squared T all over R. This is what I'm going to use to solve this problem. So that is going to be V squared over R all multiplied by T. And that is going to be equal to the mass of water is okay. Now we are looking for the mass of the water. So I will write MW, M sub W as the mass of the water. And this specific heat capacity of water is going to be 4200 times temperature change. Remember that the water boiled. So don't mistake this for the latent heat. No, they just say that the temperature of water got to 100 degrees Celsius. So I'm going to say 100 degrees Celsius minus 40. Then plus mass of container and specific capacity of the container. So we have to look for the mass of the container. So the mass of the container was not given. And the specific heat capacity of the container was also not given. Then we have to think of something different to do. And that comes with what we discussed in our previous class. When we said that the specific heat capacity, when we said that the heat capacity is equal to mass times specific capacity. So heat capacity of the container is equal to mass of the container and the specific capacity of the container. So I am going to remove these two and put it with heat capacity of the container. And according to this question, it is given as 100 joules per Kelvin. So what I'm going to do, instead of writing mass and C, I'll just put 100, all multiplied by 100 minus 40, which is the temperature change for the container, and the temperature change of water must be the same. Why? Because the water and the container are in the same place. Now, assuming I have this container, this is a container. If you notice that this container has water, this is the water in the container. the temperature of this water must be the same temperature of this container. Why? Because the two of them are together. They attain what is called thermal equilibrium, in the sense that the temperature of the liquid and container are the same, and that's enough. That's enough. So 100 minus 40 for water is the same thing as 100 minus 40 for the container. So I'm going to factor them out since they are the same thing. And I'm going to have 4200 MW, this is the mass of the water, times 60 plus 100 times 60 is going to be equal to, remember that the voltage is 220, so I'm going to have 220 squared times 120 all over 20. Remember that this V is the voltage, this T is the time was given in 2 minutes. But what I have to do is to convert it to seconds by multiplying it by 60. So 2 times 60 is 120, and that is why I have this. So I am going to have all this calculated. 220 squared so everything is going to be 48400 times, I will cancel this, 6 times 6. So everything on the left hand side is going to be 290,400, then plus this is 60 multiplied by 4200, which is going to be 252000, then plus 6000. So I'm sorry. So what I have to do is, this place is the equality sign, and then this should be the mass of the water plus 6000. All right. So let's finish it up here. So I'm going to have that 290,400 minus 6000 is equal to 252,000 mass of the water. So 290,400 minus 6,000 is 284,400 is equal to 252,000 mass of the water. So I'm going to make mass of the water the subject formula. So I'm going to say that mass of water is equal to 28400 divided by 252,000. So 20 will cancel the 20. We have 2,844 divided by 2520. And that is, the mass of the water is given as 1.13 kilogram. So this is the mass of the water for this calculation. Thank you for being part of the class. But remember, before we go, we have to take a few more questions from Examguide app. And the one we are going to be using is the UTME Examguide app. Okay, we have this first question, and we are going to take it. A block of aluminum is heated electrically by a 30-watt heater. If the temperature rises by 10 degrees in 5 minutes, the heat capacity of the aluminum is. Remember, heat capacity, not specific capacity. So, now, the one thing here is that we are not looking for the specific capacity. They say we should find the heat capacity of the aluminum. And remember that heat capacity of the aluminum, all right, okay. What I'm going to do is, first, I'm going to write my equation of electrical energy, which is given by IVT, which is equal to MC, or let me say MA, CA, and change in temperature A. This is the formula. What I'm doing is modeling the major formula is this MC change in theta. This formula is the quantity of heat. So since I'm talking about aluminum here as the metal, I'm going to now model this equation to the quantity of heat of aluminum, which is mass of aluminum, specific capacity of the aluminum, and change in temperature of the aluminum. Now, in this case, the IV is something as power times time is equal to M HA, change in temperature A. What am I doing? Remember that mass times specific capacity represent heat capacity. Then change in temperature of the aluminum, and this P is something as IV, which is the power. And the power in this case is given as 30 watts. So I'm going to say 30 times 5 times 60. Remember the time was given in meter. I have to convert it to seconds by multiplying by 60. So 5 times 60 is going to give me 300 seconds, and which is equal to, I am looking for the heat capacity of the aluminum times 10 degrees Celsius. Why am I using 10 degrees Celsius? Because they told me that the temperature rise by 10 degrees Celsius. That means they have already subtracted theta 2 from theta 1. That is what it is. So in this case, I'm going to have this, we cancel this. And this is Z0, 150 is equal to HA, which is, HA is going to be equal to 150 joules per Kelvin. And this is given as the option 90, what? This 0, this times this, multiplied by 60. That 6 must be multiplied. So I'm going to have 150 times 6, 0, 30, have 0, then this is 900. Okay, so so this is going to be 900, this is times 6, 900 joules per Kelvin, and that is seen in option C. So this one is a block of aluminum is heated electrically by a 25 watt heater. If the temperature rises by 10 C in 5 seconds, what is the heat? No, this is just still the same kind of question. Calculate the specific, okay, this one we are going to be looking for the specific heat capacity. So a block of mass 25 kg was heated from 20 to 80. So that is going to be 2.5 times specific heat capacity of the metal. Okay, that's what we are looking for, times change in temperature is going to be 80 to 20, which is 60. And all this is going to be equal to the electrical energy, which is given as the watts and the 30 minutes. So the watt is given as 120 times 30 times 60. So this 60 will cancel this 60. So I have 120 times 30, 0.00063. So 0.063. So I have 3600, which is equal to 2.5 C. So C is going to be equal to 3600 divided by 2.5. C is given as which is 1440. Do we have that? 1440. That is option C. So we now have 1440 joule per kilogram per Kelvin. Thank you for participating in today's class. You can practice more questions using the Examguide app. The app scores and gives a detailed explanation of all the questions at the end of your practice test. You can learn a particular topic of interest with different modes like study mode, mock mode, and practice mode. It also has other features that makes learning fun. It is a must-have for all serious students. Download from www.examguide.com if you don't have it yet. See you in the next class. Don't forget to subscribe to our channel, hit the notification bell and share the video to people that will benefit from it. Bye.